Geotechnical failures in earthquake zones. Welcome to Blueprint to Reality, the channel where we uncover the science and engineering behind the built environment. Today, we're diving into geotechnical failures in earthquake zones, examining how seismic activity can destabilize the ground and lead to catastrophic outcomes. We'll also explore the lessons learned and mitigation strategies that save lives and infrastructure. Understanding earthquake-induced geotechnical failures. Earthquakes exert intense forces on the ground, causing various geotechnical failures. These include soil liquefaction, slope instability, and foundation failures. Such failures often amplify the damage caused by the earthquake itself, leading to building collapses, road destruction, and even loss of life. Geotechnical failures in earthquake zones highlight the critical need for engineering solutions that account for seismic forces. Soil liquefaction, the silent culprit. One of the most significant geotechnical failures in earthquake zones is soil liquefaction. During an earthquake, saturated, loose soil temporarily loses its strength and behaves like a liquid. This leads to the sinking or tilting of buildings and infrastructure. The 1964 Niigata earthquake in Japan is a notable example where widespread liquefaction caused entire neighborhoods to collapse. Slope failures and landslides. Earthquakes often trigger landslides and slope failures, especially in hilly or mountainous regions. The shaking destabilizes slopes, causing massive soil and rock movements. The 2008 Sichuan earthquake in China triggered thousands of landslides, burying villages and cutting off vital access routes. These events underscore the need for slope stabilization and proper land use planning in seismic areas. Foundation failures. Weak or poorly designed foundations are particularly vulnerable during earthquakes. When the soil beneath a structure shifts or liquefies, the foundation loses support, leading to collapse. The 1985 Mexico City earthquake saw significant building failures due to the soft clay lakebed soil amplifying seismic waves. This tragedy emphasized the importance of geotechnical studies before construction. Case study: the 1995 Kobe earthquake, Japan. The Great Hanshin earthquake in Kobe, Japan, revealed the devastating impact of geotechnical failures. Liquefaction caused major damage to port infrastructure, while poor soil conditions led to the collapse of buildings. This disaster highlighted the importance of site-specific soil assessments and the use of seismic-resistant foundations. Mitigation strategies for geotechnical failures. Preventing geotechnical failures in earthquake zones begins with thorough site investigations. Soil testing, seismic hazard assessments, and slope stability analysis are essential steps. Engineers employ techniques like deep foundations, stone columns, and soil grouting to improve soil stability. Ground improvement methods, such as vibrocompaction, can also reduce liquefaction risks. The role of building codes. Stringent building codes play a vital role in minimizing geotechnical failures during earthquakes. Countries like Japan and New Zealand have implemented advanced seismic design standards that consider soil behavior and ground movement. Adhering to these codes ensures that structures can withstand the forces generated by earthquakes and reduce overall damage. Learning from past failures. Each geotechnical failure in earthquake zones serves as a reminder of nature's power and the need for robust engineering solutions. By studying these failures, engineers gain insights into improving designs, materials, and construction practices. From advanced soil testing to seismic retrofitting, modern technology enables us to better prepare for future seismic events. Thank you for joining us on this exploration of geotechnical failures in earthquake zones. If you found this discussion insightful, don't forget to like, subscribe, and hit the bell icon to stay updated on all things engineering. Together, we'll turn every blueprint into reality. See you in the next video.